Hello everyone, my name's Jonathan Pallant. Change things up a bit now. I'm going to talk to you about the Rust programming language. Couldn't possibly hope to cram it all into 30 minutes, so I'm going to tell you a story and tell you about a little project I've been working on, running Rust on the Beagleboard X15. A little bit about myself. I work at Cambridge Consultants. We have lots of offices all around the world. Been to quite a few of these places now. Good fun. What is Rust? So the really super quick introduction is it's a bit like a better C++. It's a statically compiled programming language. It's backed by Mozilla. They're using it to rewrite the Firefox web browser. Mozilla have a sign in their office that says, you must be this high to write multi-threaded C++. This sign is placed 8 feet high on the office wall. Writing multi-threaded C++ is tricky, right? There's data hazards. They've literally invented a language to solve this problem. The recent release of Firefox Quantum, they labeled it, rolled out their new multi-threaded CSS rendering engine. It's much faster than the old one, and it's hazard-free because the compiler can check that for you. It's based on LLVM, so we can support all of these interesting embedded targets. Things like MSP 430 are coming along, RISC-V, Atmel AVR support is coming. And it's really strong on type safety and memory safety. All these wonderful things I've heard this morning about the things C++ can do to help you make your embedded code better. Rust can help you with that as well. Plus it gives you a first-class build system, package manager, code formatter. You've got all of this wonderful modern tooling. The tagline, the sort of the pithy one-liner you tell people because honestly, everyone I meet, I tell them about Rust. I'm completely addicted to it. We say, with zero cost abstractions, you've got fast, reliable, productive software development, and you only get to pick 3. So, just a little introduction to the syntax, and then I'm going to stop talking about Rust and talk about what I did with it. So we've got generics, we've got traits. Traits are a bit like an abstract base class or an interface. You can say I take some thing T, some type T, where T meets some constraints. We can heap allocate, we can do reference counting if we want to. Typically, objects are stack allocated, and we use, I guess, like a C++ move. To move things around. We've got structs and enums, and we can do all those things. We've got closures, which is super nice. You can write routines that take a closure as an argument and call it, and we use that to good use on the embedded systems. We've got collections, we've got vectors, we've got hash maps. The key thing for embedded development is the standard library is split into 2 pieces. There is standard, STD. This requires an operating system. You must be running Windows, Mac, Linux, Fuchsia, Android, iOS, Solaris, FreeBSD, OpenBSD. You must be running an operating system. There is Core, which is the subset that works on bare metal. Core does not make any assumptions about the availability of threading libraries or file systems. It's just sort of the fundamentals. You can opt in to the memory allocator and the collections if you want to. So that's a super quick introduction to Rust. What have I done with it? Well, this was a project I undertook at work. I wanted to see if it could be done. I wanted to push the boundaries of embedded Rust, and I used this, the Beagleboard X15, not a Beaglebone. A Beaglebone has a different size. This is the big Beagleboard, and it contains this AM5728 system on chip. Recurring theme of this talk, Texas Instruments, and I guess embedded engineers in general, and naming things. I'll be honest, it's a problem. So this is the delightfully named AM5728 processor. We've got 2 gigabytes of RAM, we've got 4 gigabytes of flash, we've got some Ethernet, eSATA, SD cards, HDMI. You can make an argument this is not an embedded system, this is a computer. And yes, if you fire it up on your desk and run Chrome on it, it's a computer. I think it depends what you're doing with it. You can definitely do embedded applications on a board like this, as we'll see. So what does this look like inside? Well, there's a lot going on in here. We've got 2 Cortex A15s, so it is a dual processor, dual core computer. clocked at 1.5 gigahertz. That's some decent performance. We also have two PowerVR SGX 544 GPUs. They are completely proprietary. I have no idea how they work. They're basically missing from the data sheets. You would have to go and ask PowerVR or run their proprietary drivers. We've got two Texas Instruments C66 DSPs. These are excellent at mathematical computation. They're not so great at branching. But if there are mathematical routines you need to run, video compression, filtering and analysis of sampled RF, you could run that on the DSPs. We've got a 2D graphics processor in there, but the interesting thing is there are some Cortex M4s. So now we can see, well, we've got some Cortex A's. These are good for running Linux, good for networking, and I've got some Cortex M4s available. Well, I can do my hard real-time over here. It's really hard to do hard real-time on Linux because stuff gets in the way. Whereas if I've got a whole dedicated processor to run whatever it is, look for the incoming interrupt, look for the signal on the wire, analyze some packet. Well, I could do that on its own little dedicated core, and then they share memory with the rest of the CPUs. And if that's not enough, TI also throw in two, and I said they were good at naming, PRUICSS units as well. That is the Programmable Real-Time Unit and Industrial Communication Subsystem. Snappy. But they're like even smaller than a Cortex-M. They're like really simple microcontrollers. You get a couple of those as well. The chip itself is about $50, which I don't think is too bad considering, you know, what you get. So how do we get these processors to talk to each other? Well, this uses a system called Remote Proc. This is a standard built into the Linux kernel, and it is a generic mechanism whereby Linux can program, boot, and control remote processors for some value of remote. And normally they mean it's another core in the same silicon package. This is all defined using the device tree. If you've not seen the device tree, this was the kernel's answer to the problem that every single ARM board needed a custom kernel built for it. With a PC, there's a BIOS, and you can run some generic code that asks the BIOS, what hardware do I have? There's some mechanism to discover the hardware. With ARM systems, that doesn't exist. And so people would, the kernel that ran on, you know, the Beagleboard would not run on a Raspberry Pi or would not run on something else. Well, the device tree is a generic way of saying, this is the tree of stuff in my system. I've got 4 UARTs, I've got 3 SPIs, they're at this address, load this driver. I've got a video processor, it's at this address, load this driver. And it's the same for the remote proc. There are entries in the device tree that say, I have got these remote processors, load this remote proc driver, and this is where you get the firmware. The Cortex-Ms, the remote processors in this case, just load standard ELF binaries. I don't really have to do anything magic. I just compile a program, place it on the file system in lib firmware. The program must have a special section, a special ELF section in there called resource table, which tells the kernel how the addresses need to be mapped. And you have to do a slightly funky linker script. Most embedded systems expect you to have some flash at address 0 and some RAM at address 8 and 7 zeros. That's normally how a Cortex-M works. Well, here I haven't got any flash. I've just got RAM, because the whole system is running out of DDR. So I've got some code at address 0, which is in RAM, and some code at address 8 and 7 zeros, some data at address 8 and 7 zeros, which is also RAM. So a little bit of funky work with the linker script. And you can do what you want. You can run an RTOS, you can run bare metal. It's a chip. You can do what you want with it. The resources the remote processors get to use, a couple of different categories. You can give it what's called a carve-out. You can literally carve out a piece of system RAM, like doing a malloc of 16 megabytes, and say, right, that is for the embedded processor to use. You can hand over memory-mapped peripherals. You can say, UART3 is at this address. I'm going to give UART3 to my Cortex-M4. It has full control over this peripheral. Linux is going to ignore it. If you do that, remember to delete UART3 from the device tree. Otherwise, both Linux and your embedded processor are trying to write to the same peripheral at the same time. You're going to have a bad time debugging. You can create these shared text buffers. So this is a place where the embedded processor, the remote processor, can write text. And on Linux, I can just cat sys class device, some special file name, and I can see the contents of the text buffer. Super useful for debugging. I can just run a tail over my SSH, and I can see real-time output from the embedded processor. And from the embedded processor's point of view, it's super fast. It hasn't got to wait for data to go out over a serial port. It's just writing to RAM. And then the real interesting thing, these things called VirtIO rings. We'll get onto those in a bit. So I said Texas Instruments have interesting problems with naming things. This chip has a lot of names. If you go through their very large software developer kit, as I had to, you will find this chip, the AM5728, is also known as a VAIU. VAIU? Don't know how that's pronounced. Some of the source files are called VAIU.c. Sometimes the source files refer to a Citara, which is their commercial name. Some of the source files refer to it as an OMAP5, because this is based on their old mobile phone silicon that they don't sell anymore. Some of the source files refer to it as a DRA7X, because it turns out to be exactly the same chip they sell to car stereo manufacturers. As far as I can tell, it's the same. I'm running the same drivers. But as you go through the SDK, the source files you're looking for will have one of these 5 names to give you some hint of what you're looking for. If you just try and search for AM5728, you are not going to find all the interesting stuff. There is some upstream support for remote proc in the kernel. I tried it, it was incomplete, so I was using TI's kernel tree, and that supports loading all the processors on the system. And you get this example code. They have examples running QNX on the Cortex M4, or using TI RTOS. Their build system appears to be based on some sort of JavaScript style syntax, and I'll be honest, there's a lot of magic going on. I went through it, and I'm trying to understand how it works. There's not a lot of documentation. There's a few bits on the wiki. But I have a lot of questions. How do these processors talk to each other? Where does the code come from? What is a V-ring? What am I doing with all these memory management units? Because there's a lot of memory management units. Like, how does the Cortex M4 even boot? I understand how to boot a normal Cortex M4. I put some firmware in Flash, and I have an interrupt vector table at address 0, and you have a stack pointer, and a reset vector, and some interrupt vectors. And I understand that. I went through the disassembly of the code they generated. I couldn't find that, I'll be honest. Let me explain what's going on. So it turns out that 2 Cortex M4s, they actually both boot from address 0 simultaneously. The datasheet tells you not to do this. TI's kernel driver does it anyway, takes them both out of reset at the same time. So they're running the exact same reset vector at the same time with the exact same stack pointer. This is not going to work. Turns out they run some magic code, and the cores can work out which core they are. One is core 0, one is core 1. They are identical, except for one magic register. On core 0, the magic register returns 0. On core 1, the magic register returns 1. This magic register is not in the datasheet. There are 8,500 pages in the datasheet. I can't say I've read all of them. I've read a lot of them. I've searched for, I know what the address is. I've searched for the address. It's not in there. It's in the private address range of the Cortex M4. It's basically a secret that I'm happy to share with you because I have spent 6 weeks disassembling Texas Instruments firmware. You're very welcome. So we actually have to do some ARM assembler shenanigans because we've got this problem with the stack pointer. What we're going to do is we're going to sleep the core we don't want. So this is the boot code. Took me a long time to find it. It's got a weird name. I think it's, oh, Ducati. There we go. There's another name for the chips, also known as a Ducati. So this was hidden somewhere. This is the boot code. Can anyone tell me where the interrupt vector table is? You are looking, this is the code that is linked at address 0. This is the world's smallest Cortex-M interrupt vector table. You see those 2 longs at the top? The first one is the stack pointer, and the second one is set to the value of the function that basically immediately follows it. Those are the first two entries in an interrupt vector table, stack pointer and reset vector. Where the interrupt vectors should be, they've left them out because they weren't using them. They've just put the rest of the boot code over the top. So if you go looking for a big table of like 64 numbers, you're not going to find it because there's only two of them and they're at the top of the screen. So this is how the chip boots. It reads that reset vector, it executes it, it reads the magic register, which is addressed EOOFFFEO. I told you I looked for it in the data sheet. It's not there, but that's how it works. This is nonsense. I rewrote this in Rust. When I put my reset vector and wrote it out in code, I called my reset vector, and I put it in a linker section called vectortable.resetVector. It's just the kind of embedded programmer I am. I like to label things with what they actually are. The reset function I called reset. This magic peripheral register, I gave it a name, and we can do this in Rust. Yeah, it's got some safety, but I can declare my functions as unsafe, which means, yeah, you get to play with pointers. So here is my pointer to a register, and I can do a volatile read. Interesting difference actually between C and Rust. In C, you make the variable volatile. In Rust, it is actually the access you make volatile. It's a standard pointer, but I do a volatile read on it. That's what I'm doing. I'm reading from the register. If I don't get 0, basically go to sleep. There's some inline assembly, I can do that. Otherwise, I'm going to go and reset my memory and jump off into main. So even if you've not seen Rust before, I hope you'll agree with me, I hope you take away from this talk, it's kind of readable. It's not too bad. It's a bit C-ish. So, memory management units. Oh my goodness. This system, I think, has 12. I sort of lost count. And a number of them have to work. So on the right, this MPU, that's the Cortex A15. And on the left is the IPU, that's our Cortex M4. And every time the addresses go through a memory management unit, it's basically rewriting the address to a different value. But just to make things more interesting, the level 1 attribute AMMU that the Cortex M4 is using is also called a unicache MMU. The datasheet sort of uses either term interchangeably. So you can search for AMMU in the datasheet and think you found all the documentation, but you also have to search for unicache MMU to get the rest of the documentation. They're the same thing. They operate a level 1 cache, but there's also a certain amount of address translating. Who here is familiar with bit banding? So it's this region of Cortex-M address space where every 32-bit space in my address actually only affects a single bit at a time. It's really useful for doing atomic stuff because I can do a 32-bit write, but only one single bit of memory is flipped, and I can do that in a safe fashion. Super useful feature built into every Cortex-M at a specific address. It's specified by ARM. These addresses are bit banding addresses, and magic happens here. Texas Instruments put several peripherals on this chip which have the same addresses as the bit banding region, which means if you attempt to write to them, the CPU goes, you're trying to do bit banding, and changes your 32-bit write to a single bit write somewhere completely different in memory. So they are impossible to access unless you use the memory management unit to translate all the addresses. I basically just had to read all of TI's code, reverse engineer all the memory mappings they were doing, and re-implement that in Rust. Resource tables. So this is the magic structure you need to put in your firmware, which tells the Linux kernel what to do with this piece of firmware. So this is defined by the Linux kernel as a structure in C, and I had to write a Rust equivalent that I could put into my Rust program. Well, that's fine. Rust by default is free to reorder your structure members. If it reorders your structure members, you are going to have a bad time debugging. There is a magic marker I can put at the top. This repr line, say repr C, basically tells the compiler, lay this out like a C compiler would, which means don't reorder anything, do the kind of padding that a C compiler would do. And that's all I have to do. I've put it in the resource table section. I can basically transliterate the C structures from the C header file into Rust. There are tools that can auto-generate this. I did it by hand. And it's a pretty nice system. There's a header, and then there's a bunch of blocks, and each block describes a different feature. I've got a virtual device, I've got a V-ring, and so the R type basically says the type of that section, and then the information that follows is specific. This sort of, C-style object orientation. That's what we expect from the Linux kernel. So that's fine. Anything I can do in C, I could do in Rust. If I'm re-implementing Linux kernel structures, I think it's a fairly sound argument. The trace buffer. So in that resource table, I can say there is a trace buffer. It is at this address. And all I have to do is put some null terminated text at that address, and then in the kernel, in Linux world, I can just run this cat command, and my text appears. Not entirely clear what the encoding is. Let's assume it's UTF-8. Everything's UTF-8, right? So all my Cortex-M4 needs to do is append to this text buffer. I've allocated, I think, 32 kilobytes of memory. Interesting problem when the buffer gets full. You could sort of scroll it. You could sort of read some text from the top, move everything up, but how much do you delete? Do you delete a line? Do you delete a sentence? So in the end, I just said, well, if you get to the end, if there's not enough room to append your message, just erase the buffer and go back to the beginning. And that's fine. I can use this sort of watch command, and I'll just get the most recent text out. It's super useful for debugging and really high performance. Now, these Virtio V-rings, these are the magic, really. These were an open standard designed originally for operating systems to talk to virtualized hardware. So if you create a VM, in your VM you add a virtual network device and a virtual SCSI card. To the guest operating system in your VM, they have to look a bit like hardware, but obviously there's no actual card. I didn't put an actual network card in my computer. They're completely virtual. So there is this mechanism called a Virtio V-ring for exchanging information in shared memory, and that's how these network adapters and SCSI devices are implemented. There's a standard on the IBM website. You can go and have a look. It's really nice. The takeaway here is if you find yourself needing to exchange information in shared memory, just use Virtios, because as a circular buffer system, they're really neat. We basically have a bunch of descriptor entries. These describe our blocks of RAM. I might have 100 blocks of 1 kilobyte each. These descriptor entries are in an array. I put the array indexes into my rings. I have 2 rings, one for information going down into my remote proc, and one for blocks coming back out of my remote proc. The rule is they go down full and come back empty, or they go down empty and come back full. You are not allowed to send data down, mutate it, and send it back. It's always empty and full, or full and empty. And all I do is I put the index in the used ring and increment the counter that says how many are in there. And I send an interrupt. My M4 wakes up, it looks at the used ring, goes, oh, this number is larger than I remember it being. Data must have been given to me. Uses the index, grabs the pointer, runs some address translation, access the block, read or write from it, put the index into the available ring, increment the counter, send an interrupt. Linux wakes up, goes, oh, this number is not the value I remember it being. Someone must have placed data on my available ring. The really cute thing is the indexes that get written to the rings that say how many items are on there. Normally with a circular buffer, when you get to the end, you wrap around and point to the beginning. These indexes keep going. They increment all the way up to, I think they're 16 bits. And you take the modulo when you do the access. The reason, it's a subtle difference, the reason this is useful is you can now tell the difference between an empty and a full ring because the values don't wrap around immediately. You can go, they have the value 95, I had the value 93, therefore they are 2 ahead of me. I don't have to do any modulo arithmetic to work out how many I need to read. I just go, theirs is 5 more than mine, I must do 5 reads, and now we line up. But have a look at the documentation if you need to do shared buffer ring buffers, because they're really cute. So I said interrupts. Well, the way the interrupt system works is there's actually a mailbox. And the mailbox is, it's a lot like an American-style mailbox. You can put things in it and set a flag. It says, yep, mail has arrived. And then the other processor can look and say, ooh, the flag's up. I will go and fetch the mail. And the mail can be one 32-bit value. There are 13 system mailbox peripherals. It would be nice if they were all the same. One of them's larger than the others. So one of them has 4 users and 12 FIFOs. The rest of them have 3 users and 8 FIFOs for reasons I was not able to work out. They look like this. Their data sheets aren't too bad from a diagram point of view. And the idea is every FIFO should have one reader and 1 writer. If you have 2 people checking for the mail, then you've got a race hazard. And it's impossible to say who's going to get there first. And the other processor will go, oh, I saw the flag up and I went outside, but the mailbox is empty, crash. So you have 1 reader and 1 writer. And then there's a massive interrupt crossbar that works out which processor gets woken up when things are put in the mailboxes. There are 12 CPUs on this system, and it's designed that there's a mailbox for any CPU talking to any other CPU in either direction. It's a big system. Yeah, more documentation fun. Sometimes when TI are talking about these FIFO structures, they call them mailboxes. And sometimes when they use the word mailbox, they mean the entire peripheral containing 12 FIFOs. You can only work out which one they're talking about through context. You just have to read the documentation like 6 times and make notes in the margin and work out what they're talking about. How they work out which processor uses which mailbox to talk to which other processor, as far as I can tell, is magic. Maybe it's sufficiently advanced technology, I don't understand it, but what I found was an auto-generated C file containing an array with 144 entries, and each entry was basically a random number. There was no rhyme or reason to it. I just had to put in my Rust code, I'm very sorry, I don't know where this random number comes from, but I'm on CPU 7 and I want to talk to Linux running on CPU 0, so we're using mailbox 9, hooray. Why, I don't know. Magic happened. In terms of compiling the firmware, well, it's a bit like compiling a standard Rust application. If you've not seen it, the Rust build system is called Cargo. Yeah, sorry, the Rust community is full of puns. The modules you build with Cargo are called crates because you can ship them around. Yeah, sorry. So you run Cargo build, and then we can give it a thumb target because we're building for ARM. Rust is a cross-compiler by default. So yeah, as I said, it's a lot like standard embedded firmware. The vector table's at 0. We've got a section for our RAM. We have to have a special uncacheable section, which is where we must put our shared memory buffers, because if you access them through cached RAM, you're going to have a bad time debugging, because the Cortex M4 puts something in RAM, and then Linux looks at it and goes, nope, not there. So yeah, there we go. There's another top takeaway tip for you. If you've got 2 CPUs sharing some RAM and exchanging data, turn the caches off for that reason, for that particular region. So that's the embedded side covered. Well, on the Linux side, I can run Rust code on either. On the Linux side, your programs use sockets. It's kind of nice. You just create a special type of socket with a special source and destination address, and that allows you to send messages to any of your remote procs that you've booted up. I do a socket write on the user space side, my embedded chip gets woken up with an interrupt, looks in the mailbox, there's data in the ring buffer. It puts some new data in the ring buffer, hits the mailbox, Linux wakes up, select comes up with a socket write. So it's really nice on the user space side, just doing socket I/O. It's great. Really simple to get set up. And I know I'm not going to have problems with, trying to deal with all the pointers and everything myself, because it's been thought about carefully by people who are smarter than I am, and I can just trust them. So that's all I've got to say. The source code will be available at github.com/Cambridge Consultants as soon as I've run git push on my laptop, because I only got permission to publish it the other day. But there you will see the user space program, so a Rust application that uses RP message sockets, and you will see all of the bare metal code to bring up Cortex M4. If you've got any questions, you can find all of my information on keybase.io/thejpster. I recommend you have a look at the Rust Embedded GitHub. I think everyone has a little takeaway leaflet with loads of interesting Rust Embedded URLs. You can find me on Twitter, you can find me on IRC, and have a look at Cambridge Consultants Careers website. Lots of interesting stuff on there. Thank you very much for your time.
Any questions?
So I think almost all of the Rust code that we have seen now was in unsafe blocks. Did you actually get to the point at one point where you could use like proper safe Rust, and how long did it take you to get to that point?
Yeah, it's a good question. I showed you the unsafe bits because they're the interesting bits. It's basically booting the chip and accessing hardware. I've got to do it through raw pointers, but you almost always hide that behind a safe API. You work out what a reasonable interface is, and that interface is written in normal Rust, safe Rust, and then inside we go, okay, here's an unsafe block. I know this is the address of my shared buffer. I'm going to dereference that address. I'm going to add a little comment here that says, I've checked this address. You can find the value of this address in this data sheet on this page. And so in well-written Rust code, the unsafe block should be sort of annotated to say, I know what I'm doing, believe me. Because that's what unsafe is. Unsafe is a word that says to the compiler, leave me alone, I know what I'm doing. Which is fine, as long as you do know what you're doing. It's not something to be scared of, because every C program and every C++ program is basically all unsafe. So the fact that I can reduce the scary bits down to small sections, I think is better.
Thanks.
Other questions?